Okay, so this is the chi-square test video. So there are two types of chi-square tests. The first is goodness of fit test, and the second one is a test of independence. So how do you recognize which one you have to do? So if you have a single measurement variable, you use your goodness of fit. And if you have two measurement variables, you use your chi-square test of independence. So this is basically used to decide if, so goodness of fit is basically used to decide if one variable is likely to come from a given distribution or not. So for a very simple example, I've written is that if you want to decide if bags of candy have the same number of pieces or not. So you only have a single measurement variable right out here, which is like the number of candy pieces in the bags or not. So your null hypothesis is that the proportion of flavors of candies are the same, and the second one is proportion of the flavors are not the same, right? So there's only one variable is likely to come from a given distribution. So there's only one variable, that is the proportion of flavors of candy. Now the second one is your test of independence. So that is basically used when you have two measurement variables. So this is used to decide if the two variables are related or not. So the first example I've given here is that if you want to figure out if a moviegoer's decision to buy snacks is related to the type of movie they plan to watch, right? So there are two variables. The first variable is the will they buy snacks or will they not buy snacks, or the second variable is the type of movie that they're planning to watch. Right. So your null hypothesis is basically the proportion of people who buy snacks is independent. So basically, whether you buy snacks or you don't buy snacks is not dependent on what type of movie you're watching. So if I'm watching horror movie, it does not mean that I will buy snacks or not buy snacks. So there's basically no relation between the two variables. And the alternate is that, yeah, so if I'm watching a horror movie, I will buy snacks. But if I'm watching a comedy movie, I will not buy snacks. So that is basically your null and your alternate hypothesis. Okay, so now I will share my Excel sheet. Okay, so the first one I'll be solving is your test of independence. So this was basically the movie and the snacks wala example. So in this example, basically they are saying that, marketing firm is producing detergents, and they want to study the consumer behavior and they want to see if like the income level of the people, of the consumers, is like they want to see basically if like the brands and the income level is related or not. So they have said that there are 4 brands in the market. 1 and 2 are your premium, and 3 and 4 are your economy brands. So they want to see if you're from a lower income, does it affect what type of brand of detergent you're buying or not. So this is basically the table that they had given. So they have said that so this is also a random sampling procedure. Okay. Yes. So these are basically like from the lower income, 25 people preferred brand 1. From the upper middle, 22 people preferred brand 4. Okay, so this is what the table basically means. So now the first step that I have done is I've found the total of all the columns and all the rows. And I have found out, like, I just wanted the 600 basically means that there were 600 participants in the survey in this thing. So basically 600 people were taken as a sample. Now my step 1 is going to be my null hypothesis. So null hypothesis is basically that there is no association between brand preference and income level. So yeah, and your alternative, there is association between brand preference and income level. So regardless of what sum it comes, basically your null hypothesis will always be there is no association. And your alternate hypothesis will always be there is association between the two variables. The level of significance is 0.05, which I have assumed to be 0.05. My degrees of freedom is 9. So 9 basically comes from your number of rows minus 1 into columns, number of columns minus 1. So I have 4 income levels and I have 4 brands. So that is 4 minus 1 into 4 minus 1, that is 9. Now we find the critical values. This comes from the table. So I'll share the table. Okay. So this is how my chi-square probability table will look like. So basically, we will be seeing my 0.05 is my level of significance, and my degree of freedom is 9. So that is 16.919 is the critical value. Right. So that's my critical value that I got from the table. Now I have to create a table for my test statistic. So basically, the first thing I've done is I've copied this table where I found out the total and everything. Now, okay, yeah. So now this table is basically this formula. Okay. So this formula is basically you will be multiplying your total of the column total into your row total, and you will divide it by your total sum of all the consumers. So that is 600, right? Your total sample size. So 165 into 160 divided by 600. So let's see. So this is something that we should do for each and every values of these have to be converted into these values. This is basically your test statistic values. Now we'll see one more example. So this this is basically your column into your row total divided by your entire total, right? So this is how you will be converting your this table into this table. Okay. So these are your okay, sorry. So these are basically your expected values is the one that you found in this table, and this table is your observed values. So observed values are the ones that were given to you. Your expected values are this. So your expected values are basically your row total into your column total. So row total into my column total, and which everything is divided by my grand total, right? So this is the formula for it. Cool. Now the step 4 is basically you'll be listing down your observed values. Your observed values are these values. And in the same way, so your 25 basically corresponds to your 44. So you'll be filling the expected value in the same way. So for supposing for 15, which is this, the expected value is 46.6. So you have to be extra careful when you're filling this table to make sure you don't mess it up. But yeah, now you're going to find your chi-square value. So your chi-square value formula is this, which is your observed value minus your expected value, the whole square divided by your expected value. So for this one, we can see it is 25 minus 44, the whole square divided by 44. So this is a pretty basic formula, which you can just put it once and then you can drag it and you will be finding the values for all of your chi-square values. The last step is to find the total. So this is the main thing that you have to find the total. So this is your chi-square value. So now we can see that our chi-square value is obviously pretty big than our critical value. So this basically means that it is outside the acceptance region. So you reject your null hypothesis and you accept your alternative hypothesis, right? So our null hypothesis is being rejected. That means our null hypothesis was that there is no association, but and your alternate hypothesis was there is association. So that is what I've written. But time preference is highly associated with income level. Cool, which is something that I think all of us know. So this is your test of independence. Now your goodness of fit is this. Cool. So yeah, so goodness of fit is basically, as I said, that there's only one single measurement unit. So yeah, so you can see the frequency is just, there's just one table out here, whereas test of independence had multiple. They had an income level and they had brands. So that was like two measurement variables. I just have one. So the number of computer malfunctions per day is assumed to follow Poisson distribution with mean of 1.25 per day. So your mean of 1.25 per day basically makes up your lambda value, which is, yeah, okay. And the data as per 260 days record is in the following table. Okay. So they are basically saying that how many days, so 0 is basically the number of computer malfunctions per day. And how many times has this happened in a span of 260 days is 77 times. So basically you've had 3 malfunctions, computer malfunctions in a day for 30 days. So 30 days pe teen every time. So in each of these 30 days, there were 3 times where a computer malfunction has happened. Cool. So this is the table. Your null hypothesis is basically there's a fit between assumed distribution and actual data. Assumed distribution and actual data, okay? And alternative, there is no fit between the assumed distribution and actual data. So these two is again constant throughout any sort of goodness of fit thing you do. Okay. Moving forward, your level of significance, I've assumed to be 0.05. My degree of freedom is 5. So this 5, I basically get it as there are 6 rows, if that's what you want to call it. So there are 6 rows. So yeah, so my DF is 6 minus 1, and I'll be finding the critical value. So, okay, so the critical value is found from the Poisson, sorry. The critical value is found out for this. So for 0.05, I have my value to be 11.07. Okay. So going back, yeah. So 11.07 is my critical value that I found from the table. My lambda value is given to be 1.25. So with a mean of 1.25 per day. Cool. Now I'll be doing the same thing. I'll be listing down. So my frequency is basically my observed value. So I'll be copying down this table down here. Right. Now the next step out here, we have to find our probabilities. Okay. Probabilities for a Poisson distribution. So this is basically, you can find it from the Poisson distribution table. So I'll share that with you all. Okay, so for this. So basically, the top values, so 1.1, 1.2, 1.3 are basically my lambda values. So the lambda values that we have been given is 1.25. So out here, they don't have 1.25 values. So what you normally do is you take the mean of these two values. So you add these two and you divide it by 2. That's how you find your 1.25 values, right? So your Poisson probability for 0, 1, 2 has been given here. So this is where you get your Poisson values from. Now going back to the table. Yes. So this is how I get my values from that table. So till here, you'll be able to directly copy for 4. Now for plus 5, we will not be copying it from the table itself. You will have to subtract it from the top values. Now why we are doing this is basically because this is not 5. The number is not 5. It is more than 5. So basically for any value more than 5, it has to be subtracted for the values that are less than 5, which is 0, 1, 2, 3, 4. So you're doing 1 minus the summation of these values is how you find your 5 plus value. Cool. Now your expected value is basically your total of your observed values, basically your sample size, into your Poisson distribution values. So 260 into this. Cool. So this is how you find your expected values. Now the formula remains the same for your chi-square test. O minus E square upon E. Cool. So observed value minus my expected values ka whole square divided by my expected values. Cool. So this is how I find my chi-square value, which is the summation of all of these values. Now we see that our chi-square value is 2.7 and our critical value is 11.07. So obviously 2.7 is less. So that means my chi-square value is lesser than my critical value. So we can now assume that it lies in the acceptance region. So we accept the null hypothesis. Now the null hypothesis was there is a fit between the assumed distribution and actual data. So that holds true. And the end goal of this was to figure out the number of computer malfunctions per day follows a Poisson distribution. And that is your end. So yeah, this was your chi-square chi-square testing. So there are two testing: test of independence and goodness of fit. These two sounds are pretty easy compared to ANOVA. It's not even lengthy. So yeah, just have a template ready and you will be good to go for both of these sums.